Let's discuss what's called the colligative properties of solutions. Now, please note, colligative properties are no longer required studies for the AP exam. However, it is assumed that you have learned this in first year. So when you go into college, you want to make sure that you have some understanding of the changes that the various properties of solvents undergo when they've got something dissolved in them. There are some properties of solutions that are different from those of the solvent. First of all, the freezing point of solutions is lower than of the solvent. For instance, ethylene glycol is used to prevent radiator freezing. That's traditional antifreeze. They now use propylene glycol more frequently. Propylene glycol depresses the freezing point of the water in your radiator without using a sweet liquid like ethylene glycol that animals would lap up and die from. Moreover, the antifreeze also elevates the boiling point of solutions, so the same function can be seen in radiators. They are prone to overheating and freezing, so if you raise the boiling temperature and lower the freezing point with the same chemical, you can get an improvement in the operation. Colligative properties are defined as those properties that depend on the concentration but not the identity of the dissolved particles. And we see these are vapor pressure, boiling temperature, freezing temperature, and osmotic pressure. You can do a thought experiment. It can be done in reality, but it takes many days. If you take a sealed bell jar, here symbolized by this red rectangle, and put a pure solvent in one beaker and a beaker with a solution using the same solvent in another, and they are in the same region of space here, leave them open for a few days or weeks, you will find that after a few days, this is almost empty. The solution has almost all of the solvent in it. What has happened? The solvent has migrated to the solution. Now, needless to say, this is a solvent with a vapor pressure. The vapor pressure of the solvent, then, must be greater than the vapor pressure of the solution. There is no other explanation to have these molecules in the solvent, pure solvent, migrate over to dilute the solution further. So molecules must be leaving the surface of the solvent faster than they are leaving the surface of the solution. And as time goes on, you can see the solution getting bigger and the solvent getting smaller. Moreover, we find that the vapor pressure lowering is directly proportional to the concentration of the solute, and it doesn't depend on what solute is being in there. Solute molecules at the surface of the solution then must be keeping some of the solvent molecules over here from evaporating. For instance, the vapor pressure of 1.0 molal glucose, and molal refers to the moles of solute per 1,000 grams of solvent. Glucose is the same as a vapor pressure of just 0.5 molal sodium chloride, or the vapor pressure of 0.33 molal sodium sulfate. You see a pattern developing here? Or the vapor pressure of 0.25 molal sodium phosphate. If pressure A is equal to the vapor pressure of the solution, and XA is the mole fraction of the solvent, and P0A is the vapor pressure of the pure solvent, then we find the PA, the vapor pressure of the solution, is equal to XA, the mole fraction of the solvent, times P0A, the vapor pressure of the pure solvent. This is Rayle's law. and is well known both physics and chemistry and also in biology. For example, the pressure of pure water is 20 torr at a given temperature. If we add a non-volatile solute so that the mole fraction of water is 0.8 and the mole fraction then of the solute is 0.2, they have to add up to be 1, then the pressure of the solution is equal to the pure pressure of the water times X, 20 torr times 0.8, and now we have a vapor pressure of 16 torr in the solution. Sample exercise. Glycerin is a non-volatile, non-electrolyte with a density of 1.26 grams per milliliter at 298 K. Calculate the vapor pressure at 298 K of a solution made by adding 50 milliliters of glycerin to 500 milliliters of water if the pressure of the pure water at 298 K is 23.8 torr. Now you should be able to do this using Rayle's law. You'll need to calculate the number of moles of each, the glycerin and the water, before you use Rayle's law on it. The moles of glycerin are calculated here, 0.684 moles. The moles of water are calculated here, 27.8 moles. Now that we have the number of moles, we can use Rayle's law. X of water is the moles of water over the total moles, not just the moles of the water. So 27.8 moles of water divided by the sum of 27.8 plus 0.7, you should have parentheses around here. So 0.976 is the mole fraction of water. The pressure of the water is going to be equal to the mole fraction we just calculated times the pressure of pure water at that temperature. And so the answer is 23.2 torr. We've lowered the vapor pressure by 0.6 torr. Here's a practice exercise for you to do, and then turn off the video and check your answer later. And here's a solution to the practice exercise. Now, do all solutions obey Rayle's law? Well, if we're asking the question, we know what the answer is. No. Those that do are called ideal solutions. Those that don't are non-ideal solutions. Chemists are not terribly creative with their naming. Intermolecular forces between the solvent and the solute may be weaker than those between the solvent molecules and other solvent molecules, or between the solute molecules and other solute molecules. If that's the case, then we're not going to have the same attraction. So in this case, the solvent vapor pressure would be greater than what Rayle would predict. Now, those that don't are called out non-ideal solutions. Will we go in the other direction? Well, some intermolecular forces between solvent and solute may be stronger than those between the solvent molecules or between the solute molecules, in which case the vapor pressure would be lower than what Rayle predicts. So you can have non-ideal solutions in both directions with the vapor pressure of the soluted solvent either greater or lower than what is predicted by Rayle's law. Now what happens to the phase diagram of water when you introduce a solute? Well, remember what water's phase diagram looks like. Temperature versus pressure here, and here we go with the solid to vapor, the liquid to vapor, and the solid to liquid interfaces. We find that since the vapor pressure of the solution is lower than that of the pure solvent, then the freezing point is lower for the solution, and the boiling point is higher. That's why antifreeze works in both directions. What's a molecular explanation? Well, crystals of a pure solvent separate out to form the solid. Solute molecules are not soluble in the solid solvent, so the triple point must be lowered. If so, the freezing point is lowered, and that delta T for the freezing point lowering is some constant times the molality. The vapor pressure of the solvent is depressed at the normal boiling point, so it won't boil at the normal boiling point. You need extra energy to eject all the liquid molecules in the gas phase, and the delta T for the boiling point is equal to some constant times the molality of the solute. Now here are the constants for the most common solvent, water. The freezing point depression is 1.86 degrees Celsius per mol, and the boiling point elevation is 0.52 degrees Celsius per mol. Constants for other solvents are given in various tables on the internet or in your textbook. Here's a sample exercise for you to do. And here's the solution. For 1,000 grams of solution, 250 grams of ethylene glycol, 750 grams of water. The molality is the moles of ethylene glycol per 1,000 grams of water. So we divide 250 by the molar mass, 62.1, and get 4.02 moles. The molality then is 4.02 moles over 750 grams of water times 1,000, 5.38 molal. Molality is 5.38. We put that into the boiling point elevation expression, and we get 2.8 degrees. We plug the same molality into the freezing point depression equation. We get 10 degrees. So the boiling point would be 102.8. The freezing point would be minus 10 degrees Celsius. Now you know why people sprinkle salt on their sidewalks when they think things are going to get freezing rain. That depresses the freezing point considerably. And remember, each sodium chloride breaks up into one sodium and one chloride, so you get twice the bang for the buck. And the temperature of freezing then for that salt water would be much lower than 0 degrees Celsius. Osmosis. Osmosis is diffusion across a semi-permeable membrane. You've heard of that, of course, in biology. Small solvent molecules will pass through. The large solute molecules will not go through in the other direction. Osmotic pressure is measured as the pressure on the solution that stops the net movement of solvent across the membrane. The net movement of solvent in the osmosis is toward the solution with a higher concentration of solute. You learned that in biology. Pi is the way we symbolize osmotic pressure. That's N over V times RT. So the molarity now times R times T is the osmotic pressure. Two solutions are isotonic if they have the same osmotic pressure. If solutions are different in pressure, the one with a higher concentration has a lower pressure, is said to be hypotonic with respect to the other. You may see this used in a biochemistry class. The biological implications are clear. If you put your hand in fresh water for half an hour or an hour, it'll crinkle up. High salt intake causes swelling of tissues. Honey is antibacterial because it has a high glucose concentration, and the bacterial cells can't survive in it. And of course, you remember active transport, low concentrations of things that your body needs can move to high concentrations across a cell membrane, but you need ATP to make that happen. You need a proper pump. Commercial applications are clear. You can get reverse osmosis machines to purify your tap water, desalination, and coastal regions.